Okay.
Okay, so thank you all for coming to this first talk of the fall of 2022 MOPA, and it's my great pleasure to introduce Athar Abdul-Quader, who has his PhD from Graduate Center, CUNY. He got his PhD in 2017, and he's now speaking to us either from his home or from SUNY Purchase, where he works. And also for the last 3 years, he was really the chief organizers of these seminars, and everything went very well. So I want to thank you, Athar, for all the work that you put into this. And today's talk, as you can see, will be about pathologically defined subsets of models of CT minus.
Okay, thank you for those kind words, Roman. I'll say I really don't do much of any organizing. It's really mostly people responding to me because I CC Roman on the email. So it's borrowed glory, if that. Okay, so I'm going to talk about models of CT minus with certain pathological subsets or pathologically defined subsets, however you want to say it. So I guess so. There's a few places I can start. So first of all, I'm going to say I'm not going to get into certain technicalities about the differences between truth predicates and satisfaction classes. So for my purposes, I'm really just going to talk about full satisfaction classes. And there's several people in the audience who know about the technicalities implicit in sort of translating between languages of satisfaction classes versus truth predicates. That can speak to that better than I can. So I'm not going to get too into the weeds on that. 1 second. Okay, so what I will say. I guess I'll start just by saying, in my mind, a model of CT minus. So CT minus is sort of a theory that expresses of compositional truth. Of a compositional truth predicate. So in my mind, I have sort of a model of PA and a subset of that model, so that's a sort of a full truth predicate, a full compositional truth predicate. And so again, if you prefer to think in terms of satisfaction classes, sort of feel free. So I'm not really going to talk too much about the differences there. So sort of there's a lot of history that I can go through. I'll kind of skip over some of the history, but I'll say I'll hit on some of the most important things. I guess before I start saying anything, I should say again, this is joint work with Mateusz Wewick that has been ongoing for a little while. So it's still work in progress. And a lot of what I'm going to say today is essentially due to Jim Schmerl, rephrased in in certain ways, but it essentially boils down to ideas that Jim Schmerl communicated to Ali and I about 10 years ago, and I don't think it was ever published. So we kind of unearthed that and started thinking about some of these questions. So right. So I guess I'll start with the classic theorem from Kotlarski, Krajewski, Laughlin, and then Inayat and Visser, and then others who have proven that essentially that CT minus is a conservative theory over PA. And so you could describe this in this way: if M is a model of PA, it's countable, recursively saturated. Then there is a subset of that model that is, or sort of an expansion to CT minus, a full compositional truth predicate. Okay. I guess I should also warn the audience that I haven't done a chalk talk in quite a few years. So this is my digital version of that. So I'm hoping that it goes somewhat well. But as usual, feel free to interrupt me as we go. Okay, so this is the classic result about full satisfaction classes or truth predicates in recursively saturated, countable recursively saturated models. So for today, I'm mostly going to assume, so for today, we'll assume all of our models are models of PA and are countable and recursively saturated. Okay, and so therefore expand to CT minus. Because of this result, we know that essentially CT minus is conservative over PA, right? So in other words, it doesn't prove any new arithmetical theorems. If you add induction, or if you add any kind of induction, some of that that goes away, right? So CT is the theory CT minus plus plus induction in the expanded language. In other words, it's the theory CT minus plus PA star in the expanded language. And this is essentially an exercise that if you have a model of CT, a full compositional truth, then the model must think that con PA is true. Okay. And so CT is not conservative. Right. There are recursively saturated, countable recursively saturated models that do not expand to CT over PA. And then you can sort of lessen that induction by sort of putting grades on it essentially. And so you can look at CT0, which is CT minus plus delta naught induction. And the same thing happens. You can see that CT0 proves con of PA as well. Okay, and of course, if you think about it for a little bit, you'll see it proves both of these theories prove quite a bit more. Like you can prove con of PA and con of PA and things like that. There was some work by Kotlarski at one point on full satisfaction classes and induction that talks about sort of the amount of reflection that you get, the amount of times you can iterate this, and in full, if you have full induction versus delta non-induction, and Mateusz has also done some work on that as well. All right, so these are sort of some of the main characters of today's talk. The next main character to talk about is the principle of disjunctive correctness. And that will allow me to get to this word pathologies that I had in the title. All right, so when you have a truth predicate, you are allowed then to ask questions about the truth of non-standard sentences, right? So let C be any element of M, and suppose you have a coded sequence of sentences in M, right? And sentences in the sense of M. Then the disjunction of length C of phi I is defined inductively as the disjunction of length 0 is just phi 0, and the disjunction of length n, I guess we'll call it n plus 1 of phi I is just the disjunction. It is just the sort of the left bracketed disjunction. Okay. And so now we have the ability to talk about sort of non-standard length disjunctions. And so then DC is the principle of disjunctive correctness. And it essentially states, okay, for every C and for every coded sequence, the disjunction is true if and only if there's a true disjunct. Okay, and so checking to see who else is here. So Ali is here, and he proved he along with Fyodor proved this result. That disjunctive correctness is not a conservative principle over over PA. So CT minus plus disjunctive correctness is essentially the same theory as CT0, right? And so disjunctive correctness gives you delta naught induction. And so this is somewhat interesting, but this tells you essentially that if you have a model of CT minus that does not have that level of induction, then it's going to have it's going to have some true disjunction which has no true disjunct, or vice versa. It has a sequence that has a true disjunct, but the entire disjunction is evaluated as false. So this was a very interesting result, fairly recent. I think 2019. Ali can correct me if I'm wrong on that. And then more sort of shortly after that, I think this past year, we have a result from Cesari, Mateusz, and Bartek, who kind of split this principle in half and sort of look at disjunctive correctness out versus disjunctive correctness in. So DC out versus DC in. So if you have a true disjunct, then you should be able to conclude that, or sorry, if you have a true disjunction, you should be able to conclude that there is a true disjunct. And if you have a true disjunct, you should be able to conclude that you have a true that the entire disjunction is true. And so they showed this one is not conservative, and this one is conservative. Okay, this is essentially, so again, this is due to Cieśliński, and I'm not 100% sure on the accent marks if I'm putting them on the right letter. So I apologize if he sees this later. So this is due to Cesari, Mateusz, and Bartek. And there's two parts of it. I'll just state the one that I think is most relevant for the rest of this talk, which is that DC in is conservative over PA. Sorry, let me write that properly. CT minus plus DC in is conservative over PA. Okay. So I'm not going to go through the proof of this, but the idea is quite interesting. That essentially, if you have a countable model of PA, you can build an elementary extension to a model of PA that has an expansion to a model CT minus, which makes all all disjunctions of non-standard length true. So such that for any C greater than omega, and for any VI I less than or equals C coded, and T thinks that this disjunction is true. Okay. And so this we refer to as disjunctively, or I think well, I'm not sure if they use this term in their paper, but in conversation we've been referring to this as disjunctively trivial models. This is interesting. The setup with disjunctions is it's
so
yeah.
can I, no, we should be asking questions. One
Yeah,
has
go
come to
ahead.
mind immediately. Can you make them all false as well?
No.
Oh,
I think not.
Sorry
No, go ahead.
No, that's precisely because the other direction is not conservative. You know, like if you could make all non-standard
I
disjunctions
see.
false,
All right.
then DC out would be
Then
conservative.
this would be conservative. Yeah.
Okay.
So that's
That-
actually
then this one.
that's not a yeah, that's surprising, right?
Yeah, that's interesting.
I mean,
good question. Go ahead, Wojtek. I think you were saying.
yeah. So of course this was the first idea to show non-conservative of DC out, namely to show that all disjunctions, all non-standard disjunctions can be made false. And the technical, like, well, of course, the deep reason is that this actually is not conservative. The technical reason is that, well, if you have a false disjunction, right, you have to. I would have to double
I
think.
think actually,
Can I add
I think
something here?
it's pretty simple because of the way that I defined this disjunction. By CT minus this disjunction on the left is true if at least one of these disjuncts is true.
Yeah.
But so if you have something along the lines of if you have something along the lines of some phi I or 0 equals 0. Right, this is now a non-standard length disjunction, and so that has to be true because it has a rightmost disjunct, which is true.
Yeah, you're right. I mean,
And so
yeah.
I think that there's interesting questions if you don't bracket it like this, if you do some sort of binary disjunction.
Then it's actually known to be possible.
Then it's
actually,
okay, perfect.
It's in the paper. Actually, that's in the paper. So that under binary bracketing, like if you split it equally or with many other pathological bracketings, you can arrange it so that all disjunctions are false.
Okay, sounds great, perfect. Sorry, I think I cut off someone as well who was about to ask a question.
That was me, but I was just going to say exactly what you said, so we're on the same page.
Okay, perfect.
Okay, yeah.
All right. Well, while we're here, are there any other questions about the setup? Because this is a good place to sort of to stop anyway. Okay. So again, I think it's worth sort of this is a really interesting sort of construction that you have a model of PA and then you can extend it to a disjunctively trivial model so that this side of the the right hand side of this implication is always true, and so even if even if it doesn't have a so then this implication is sort of more or less irrelevant, or this hypothesis is more or less irrelevant, and so that's sort of an interesting construction, and similarly they showed that you can you can get DC in, but you can't get DC out at the same time. So this result, I want to sort of say something say something about this. This model N that we end up getting turns out to be turns out to be arithmetically saturated, and that's where I want to pick up. So this is a result that Mateusz and I noticed, essentially due to some work by Jim or an unpublished work by Jim Schmerl. So suppose M is countable and recursively saturated. Then the following are equivalent. M is in fact arithmetically saturated. Which sort of where really I'm going to use the fact that omega is a strong cut, and I'll remind you what that means. What strength means, and M has an expansion to a disjunctively trivial model of CT minus. Okay.
Oh, so let me just say, well, you probably were going to say that anyway, that this is
Go.
this is very beautiful. So it means that if you're not arithmetically saturated, that you are forced to make some of the disjunctions true by the weakness of the standard cut. I think this is quite fascinating.
Yeah, it's fascinating. It's surprising because a lot of the results, a lot of the so the way that this result is proved, and again Bartek or Ali could chime in on this if they'd like. They use the sort of Inayat-Visser sort of technology to or technique to build this chain of models, and then and then end up with the resulting model having this property. And usually when that has been done, it ends up you end up being able to just apply resplendence and say, okay, so then M has, so if M is countable and recursively saturated, then M has the same property. It's a little strange to me that you couldn't, and essentially if you have the strength of omega, then you can. In fact, this ends up being what happens. So this is the main theorem that I want to mention. I want to advertise. Again, it's so really the credit should be to Shmuel as well, or specifically should be to Shmuel. It's kind of stuff that that we were looking at, and then Ali mentioned, oh, there's this message he had from Jim a little while ago, and then we looked at it. I was like, oh, actually this means something interesting. That let's think about a little bit. So I'm actually not going to prove this result today. It will follow as from a corollary. It will follow from something. Well, so 2 implies 1 will follow from more general results that I will show, or that I hope to show. Today, and then 1 implies 2 is essentially very similar to techniques that is similar to techniques that I used in other that I use in the other results. So I'm not gonna go through that. All right, so what will I actually show? So instead of looking at all coded disjunctions, right? All coded disjunctions, we'll look at specifically idempotent disjunctions. That was the first. So we'll make a couple of simplifications, and really it's just one major simplification. I'm only going to look at disjunctions of 0 equals 1. Right, that's the only one that I want to look at, and that's essentially because I want to see when can you make this disjunction true, and you know, if you can make it true for all non-standard C, or let me put this: if if the truth predicate is disjunctively trivial, then you can make this true for all non-standard C, and that's as much as you can possibly do, right? What happens in more generality, right? If you have a model of CT minus, so given a model of CT minus, what is the set of those C for which this is true, or for which, which it's false, right? Either one, however you want to think about it. What is the set on which the truth predicate is correct on this disjunctions of this one formula, and what is the set on which it is incorrect? So I'll start with I'll look at the correct side. Okay, so which sets X can be realized? Okay, and I'll say in our work we treat sort of essentially the generalization of this question, but for the purpose of the talk, I'm sticking to the example that that really motivated us throughout our work. But we're toward the end, I'll say a little bit about what our generalization is. But we talk, sort of, if you have a set of sentences, which subsets of that can be realized as the which subsets of that can be made true and false or whatever, and what assumptions do you need about that set of sentences in some way. So essentially the results that we use, the results that we get can apply to similar questions about sort of conjunctive correctness, or conjunctions of 0 = 1, or double negations, right, of some length, right, sort of a double the double negation of length C is sort of the negation of length 2C or something of some formula. Double negations, and then long blocks of quantifiers XC, where if this is a sentence, then adding unnecessary quantifiers should not do anything, but sort of same idea. I'll say something. So I'll stick with the example, with this motivating example, but the same results will apply to very sort of similar classes of examples with conjunctions, double negations, and long blocks of quantifiers of single formulas. And then we also treat separately the question of all idempotent disjunctions, or all idempotent conjunctions, or all all idempotent sort of operators like this. So not necessarily localized to a single formula. Okay, so first there are some obvious things about this set. So which sets X can be realized? There are some obvious things that have to happen. So clearly omega has to be contained in X. Right, that you need for it to think that all standard length disjunctions of 0 = 1 are going to be false. Okay, X has to be closed under successors, and predecessors. Okay, that comes from essentially the definition of our long disjunction as saying as this thing, right? And since we're taking a disjunction of a false statement on the right with some long sentence or some long disjunction on the left, it clearly, if this one is made clearly, if this one is made false, then this one has to be made false, and vice versa. And there is a third property, but these are the two that are sort of obvious. So it turns out that there's a third property. So also number 3, X has to be what we call separable. So this is a term that we came up with. So I'll give the definition here. For each A, there is some sort of there's a C that I think of as a separator, which says for every n in omega, C is going to tell you which of the elements of an of the sequence coded by A are in X. Okay. I guess equivalently, you could say you could have C literally code X intersect A, or up to omega. It's not, no, but this is the definition we use. Really quick lemma is that omega is separable if and only if omega is a strong cut. And this is where the idea that of arithmetic saturation comes in, right? That if I have a disjunctively trivial model, then omega will be separable in particular, and then therefore omega will be a strong cut. So just to remind everyone, a cut I is strong if for each A there is a C greater than I, such that for all n in I, an is in I if and only if it's less than C. Okay. If you go through these two definitions, it's essentially an exercise to prove this lemma. I'm happy to come back to it, but I think I'll just leave it up for a second and let people think about it. But it's essentially an exercise. If you really don't need much, I mean, essentially it's true about all models M, but it's using recursive saturation with up to sort of some bounded complexity types. But it's an exercise that when I was in grad school, Roman would have asked me to do, I assume. Okay. So here's the result that I actually want to talk about. So M is going to be a model of PA, countable, recursively saturated, and X is going to be a subset of M. The following are equivalent. There is a T such that so M has an expansion to CT minus, making X exactly the set of those C on which T is correct about disjunctions of 0 equals 1. Okay. And X satisfies the properties 1 to 3 that I mentioned above. Okay. So I'll zoom out a second so I can try to get both. Yeah, I can get everything on the screen at once. So properties 1 through 3 say that omega is contained in X, that X is closed under successors and predecessors, and that X is separable. Okay. Again, if the 1 implies 2 direction, well, it's pretty clear that the properties 1 and 2 are necessary. That if so it's pretty clear that those properties have to be in there, and then if you add in the third one, if you add in separability, you do get an equivalence. That's this idea. Okay. All right. Are there any questions or anything at this point? Should I take a break for people to catch up on anything? Okay. So then I'll go ahead. I'll say which direction do I want? So I'll come back to the 1 implies 2 direction. The 2 implies 1 direction is a little bit more involved. So that's why that's the one that I'll try to say something about. That's it's a little bit more involved. let's see how much I need to say here. All right, so as I mentioned, this is a lot of this is due to Jim Schmerl. So I'm gonna give. I'm basically going to give the treatment that Jim gave for this argument, with the modification that he was specifically looking at cuts. So I guess that's the one important thing that I should mention. There's a lot here that this is one of the things that I think is somewhat pathological about these sets X. These sets X don't need to be closed under addition, for example. They don't need to be, they have very, very, very weak closure properties. They just have to be closed under successors and predecessors. Or they just have to contain omega. Separability does not imply that it's a cut, right? So set X does not need to be a cut to satisfy this. So you might end up with a model sort of looking where you kind of pick and choose some cut and then skip another, skip some several parts, and then pick and choose sort of different sort of convex sets, I guess, that will be your separable set X. So it's sort of these sets X can be very strange and in fact pathological.
Athar, sorry, do you know how many of them are there?
How many such sets there are?
Yeah.
I haven't thought about that.
Are there continuum many?
That's a good question. I have to think about it. I don't have an idea off the top of my head, but I would guess so, that there are continuum many, but I didn't because it's it's very easy to make this to satisfy the separability.
Right. So I would think that there should be continuum many. It would be quite interesting if there were not, but
there are. Yeah, I'm not sure. I'll have to think about that for a little bit. Are there continuum many?
Yeah, I guess, but by your theorem, right? Because essentially you can make disjunctive, like this kind of disjunction falls on any cut, I guess, and there are continuum many cuts. So by your characterization that those are separable, it turns out particular that there are continuum many such sets. I mean, by your characterization,
So
it's
not necessarily any cut.
Yeah.
So for example,
sure.
if omega is not a strong cut, you can't do it for omega. Right, and so that's one of the there are some restrictions on the cuts. I think yeah, I'd have to think about it a little bit. Okay. Well, let me sort of try and outline or describe a little bit of this proof of the 2 implies 1 direction. So essentially what we're going to do is we're going to build a sequence of satisfaction classes, truth predicates, however you want to call it. So a sequence of full satisfaction classes, so not partial satisfaction, on the model M itself, and with some sort of limiting procedure. So we'll make sure that the I plus first satisfaction class agrees with the ith one on certain formulas, and then each step will sort of make it a little bit more correct on the formulas that we want it to be. Okay, so we need a few definitions. So for formulas, we say I'm going to use this symbol, the sort of triangle less than symbol, that to mean an immediate subformula. Phi is an immediate subformula. Of psi. Okay. When I say that a set of formulas is closed if it's closed under this relation. So closed downward under this relation, right? So i.e. if psi is an x, or sorry, psi is an f, and phi is below psi, then phi is an f. And then the closure of a set is the smallest closed set. Containing f. Okay. And so often I'll look at closures of single formulas or of singletons. So for example, if I have some disjunction of some length c of 0 equals 1, you just, if you look at the tree of the sort of syntax tree for this, it has it essentially is going to look like is gonna sort of be a very left branching tree, or it's going to branch sort of down to the left, and you will see essentially this will just be all the finitely many steps you can step down from this formula for n and omega, plus the rightmost disjunct, which is just the 0 equals 1 itself. Okay. So it's the closure is not the closure of a set is not necessarily definable in PA. You can think of the PA version of it, but we're gonna think externally when I say the closure of a set. And again, this is all sort of all from Jim. And then so F, a subset of F prime, generates F prime if the closure of F is F prime. And then F prime is finitely generated if it's finitely generated. So if it's generated by a finite set. Yeah. Okay. So this is again the 2 implies 1 direction. So I'm going to have an x that contains omega, is closed under plus and minus 1, like successors and predecessors, and is separable. Okay. One thing, so I guess before I move on, one thing to think about with these finitely generated sets, because so with these finitely generated sets, you essentially get something that looks like you might have a phi 0, a phi 1, phi 2, up to, let's say, phi n minus 1. You essentially will get a finitely branching tree, or a union of finitely branching trees. And so you can code the elements of these trees, right? So in other words, these are the closures of each of these. And certain things can repeat, that's okay, but if you just want the elements that are in the closure of phi 0 up to phi n minus 1, you can there's an A which codes the closure of phi 0 up to phi n minus 1, in the sense that for each psi in this closure, there is an n in omega where an is equal to psi, and for each n in omega, an is in the closure. Okay. Does this make sense? I'll take the silence as fine. Okay, so this is important because this is what this this A that we get is we're gonna then apply separability to, and so we'll sort of we'll apply separability so that we can sort of figure out whether this A has a length that is going to be an X or not or something. All right. So given all that, so given a set X satisfying properties, oops, sorry, satisfying properties 1 through 3, we build sequences F0, F1, etc. of finitely generated sets of formula such that the union of these FIs is all formulas in M. And then S0, S1, etc. that are full satisfaction classes such that the I plus first satisfaction class is going to agree with the ith satisfaction class on formulas from Fi. Okay. And there's going to be 2 more things. Each one is recursively saturated, and if you have a disjunction of 0 equals 1 in the ith finitely generated set, then Si will think that this disjunction is true on any assignment alpha, right? So assignment for any assignment for that formula, which since this has no free variables, it's essentially any assignment, if and only if C is not in the set X. Once you have this, supposing we can build these sequences, and again, this is I can't stress this enough how much I did not come up with this myself. So once you have these formulas, then or these sequences, then you can let S be the union of essentially Si restricted to Fi over I and omega. Then it should be I and omega. And if you do this, then essentially you get you'll get a full satisfaction class that does exactly what you think. What you think. It's essentially S will be full satisfaction class on M, and if you have any disjunction of this form, it will be made true if and only if that length is not an X.
Athar, can I ask
Yes.
a question here?
Yep.
So in particular, this seems like a very simple construction of a full satisfaction class. So there must be something hidden here. So is this a sort of a version of Ni and Visser then?
So it's somewhat interesting because in the literature I could not find another good example of building a satisfaction class on the model itself. So each one of these is essentially a satisfaction class on the model itself. Most of the time, the Naiad-Visser construction, you start with the model and then you build, you put in the properties that you want of that model, of that satisfaction class, and you get them in some extension. And if you can, you do some sort of reflection or resplendence to reflect back down. This I thought was somewhat interesting as a good example of building a satisfaction class on the model itself.
But it wouldn't work on any model. It has to be arithmetically saturated.
Well, if the set X we want is omega, right? If the set X is omega, right? If it happens to be that so omega satisfies properties 1 and 2 that I mentioned, but property 3, that is a separability, that requires strength. right? And so if you start with a model that's not arithmetically saturated, you could pick another x and something will happen, right? Interesting. So interestingly enough, there will be a cut that satisfies that property, but it has to be non-standard. Right? So
yeah, so I have a comment with regard to this constructions of full satisfaction class on models without changing them. Yeah, so there was not by me circulating. I think I sent it to several people, like maybe 1.5 years ago, maybe 2 years ago. Anyway, so basically there was construction that was working for all recurrently separated models to build up this yeah, full satisfaction class on the model itself without making it.
yeah, so that's the one major exception that I found was yours, in fact, Fedor. So so thank you for that. So actually, yeah, I think Fedor gave a talk, gave a couple of talks on this over the last couple of years, so there is another there is another sort of construction of a full satisfaction class, which does not sort of go which does something, you know, interesting without sort of going past the model itself. Yeah, you're right. I should have clarified that. It's not entirely it's not entirely true that say that there's this is the only one. Yeah. So I guess what I'll say is the separability is what so the separability is what allows us to essentially write down a theory that that we could then realize in an extension using an IFSR, and then come back and use respondents to stay in the model itself. And that's going to be the idea. All right, so I think I can give the idea of the result in the next 5 minutes or so, but I recognize that I'm short on time, so I apologize to Roman and to myself for running late. And anyone who needs to drop off, feel free. I'll give the major parts of this construction for the next few minutes, and then if there are questions about other things, I'm happy to take them after too. All right, so suppose we are so we have Fi and Si constructed. We have you can pick any phi not in F, so pick any phi not in Fi, or so pick the least phi not in Fi in some external enumeration of the formulas, so that in order type omega, and let Fi plus 1 be generated by Fi and phi. So then Fi plus 1 will be your next finitely generated set. You can let F prime be everything that you want to preserve plus the only things that you're interested in Fi plus 1, right? In other words, the only things in Fi plus 1 that are disjunctions of 0 equals 1. Then F prime is closed, okay? And it's not too hard to see that. I guess if you had a formula in F prime, then it's either in Fi, and so it's direct subformulas there, or it's one of these, and yeah, its direct subformula would be there as well. Okay, and there is an A which codes, and this is what I mentioned before, which codes well, in fact, I can say it can specifically just look at let A be something that codes the lengths of disjunctions in F prime, And if you want, you can say disjunctions of 0 equals 1 specifically. So again, just run down this finitely branching tree that is fi plus 1 and look at the ones that are disjunctions of 0 equals 1. Okay. And since there's an A, then there's a C, which separates it. That means that for all n and omega, an is in X if and only if n is in C. Okay, and so we're going to define a satisfaction class S prime. So by as follows. So put phi with an assignment for phi in S prime if either phi is in Fi and phi alpha was in Si, or phi is the disjunction of length an of 0 equals 1 and n is not in C. Okay. And so then the claim is that S prime is is a satisfaction class on formulas, or is compositional, or wait this way, is compositional for formulas in F prime. Okay. And then this is where we can use the Inayat-Visser construction, or the Inayat-Visser lemma, which will say that there is an elementary extension M such that n has a a satisfaction class on all formulas from M, agreeing with S prime on F prime. And then you can write down a theory that essentially says that S is a full satisfaction class plus S of phi alpha if and only if Si of phi alpha for phi in I plus, write the pluses in a consistent way, S of those if and only if n is not in C. Once you've written down this theory, essentially what you've shown already is that that this theory is consistent. Okay, and then using recursive saturation of MSI, you get an expansion you get an expansion S, right? And so there's MSIS satisfies this, and in fact you can use chronic resplendence to assume that that MS is recursively saturated. Okay. And then that's the next one. So then Si plus 1 is SS. Okay. And so like I said, once you continue doing this construction, you get the sequence of Fi and Si, and then your full satisfaction class S at the end is going to be defined as this as the union of these SIs restricted to FIs, and this will have the property that S will think that disjunction of 0 equals 1 is true if and only if that length is not in X. Okay, so again, I'll say that in our work, so this completes the proof of the 2 implies 1 direction of this theorem. I can say a little bit about the other direction if anyone's interested. In our work, we do ask this question more generally. So given if D is a set of sentences and A is a subset of D, what properties, right, can we isolate properties of A and D that that will allow us to do essentially this argument in more generality, allowing us to give the same argument in more generality. Okay, so I'll save that a little bit. I'll say again, there's much more to say. There's again, so just on separability, like I said, there are cuts that are not separable. There are cuts that are separable, that are not. There exist cuts that are separable but not closed under addition. There are cuts that are separable and closed under addition, but not multiplication. And essentially anything else that you can think of, right? If you have any two definable functions f and g, where there's any cut which is closed under f but not g, then there's a separable cut which is closed under f but not g. So I'll stop there. There's more to say. This is one part of our project. There's other things that we talk about from a sort of that are less that are less local, right? So all of the arguments that are given generalize to things that are local to a single formula. So applying disjunctions of that same formula, or conjunctions, binary disjunctions, double negations, long blocks of quantifiers, etc. There are more interesting questions that you can ask about what happens if you look at all idempotent disjunctions, or all blocks of quantifiers over formulas, and all idempotent binary disjunctions, etc., etc. And so there's different there's lots of different examples of so we refer to the examples that I talked about today as being somehow local. They're local to a single formula, whereas there's all these non-local pathologies that one could talk about as well. But I'm so already way out of time. So I'll stop here. I apologize for going a little bit over, but I'm happy to take questions about anything. If people would. Thank you.
Okay, thank you, Athar. Well, officially, I'm in charge this time, so I just ask, well, do you have any questions?
Can I ask him one quick question?
Sure.
Go ahead.
So I guess it really connects to these results that you said at the end. You said you've been studying, but you didn't address directly, which it's a question that I've often thought about after seeing and studying Jim's construction that you referred to, and that is so your construction, that construction you described takes a particular notion of being logically well behaved for a set. I guess you're looking at arbitrary sets, but Jim was looking at cuts, and the well behaved notion that you have in mind is from the point of view of disjunctions being well behaved. So have you made any advance towards the more general, a better or stronger notion of well behaved, which would have to do with, let's say, being closed under proofs, basically being closed under either tautological, propositional logic proofs, or first order logic proofs, or some such things, because there's an unpublished result of mine from years ago that in a recursively saturated countable model, there are arbitrarily long cuts on which a truth predicate can be constructed to be well behaved as much as you want from a logical point of view. And so it would be interesting to be looking at somehow
Right.
that. So
I think that's where we started. That was like the question we initially sought out to study. And I think one of the things we started with was taking essentially that argument that you just outlined right there, and along with Fyodor's construction of a satisfaction test, and we were able to show some we had some very preliminary things about, okay, maybe we can show it's there's ones where it's closed under multiplication or something. I think we thought about that for a little bit. I can't remember. It didn't go very far because essentially once I realized that there's a lot of essentially once we started focusing on more specific questions, we got very I kind of got more into the weeds on those specific questions, because these we were able to actually kind of we were able to boil down to questions about models of PA that I felt like, okay, now I know what's going on.
Okay.
And so that's where we were initially motivated by that question, essentially, what is the truth preserving cut? We were able to a lot of our our informal arguments that we gave ended up boiling down to things like, oh, what if maybe we have a model where the where truths are where proofs are bad because of disjunctions are bad or something like that.
Right.
And then that made us think, okay, well, actually let's look at this. What is the disjunctively correct cut? And so on. So long-winded answer is we thought about it, but no, we didn't actually go and make progress on that. So
Okay, thank you. It just means, I guess this said, it is an indication of how much open the field is still to
yeah.
interesting advances. Thank you.
Oh, Athar, I enjoyed hearing your talk. Thanks.
Thanks,
You did a good job.
Thanks, Jim.
That was not a question, was it? All right. No, thank you, Athar. It was an excellent talk. And as always, I want to remind everyone who's still there that we welcome talks from everyone. So if anyone has anything to say, should email me or Athar, and our schedule still have many slots that have not been filled yet. So think of something to say. And Athar, what's happening next?
Fyodor will be speaking next week. It's something about Tenenbaum's, how to escape Tenenbaum's theorem, I think is the name of the talk, and a recent paper
that's actually something quite interesting. Yes,
yeah.
I've seen that paper.
Yeah.
So we'll see you next week, and that's also at 1, right? We'll be at the same time.
Yeah.
All right.
Thank you.